Good evening, everybody. Welcome to Bhoo-Mandal talk series by IEEE-GRSS Bangalore section. So we have with us Mr. Amruth Kiran, who's going to talk about building the India data queue, lessons learned. So briefly, before we get into the talk, I'd like to introduce IEEE-GRSS Bangalore section and the talk series. Thank you all for joining us today. It's a pleasure to have you here. The GRSS Bangalore section was created in 2012 on December 24th. So we are almost finishing 10 years now. It was originated in ISI Bangalore, that is the Indian Statistical Institute Bangalore, with the efforts of Professor Daya Sagar. This chapter is meant to foster the professional community to engage in research, development, engineering in the areas of geoscience and remote sensing. So we have the slate that took over in 2021 on January 1st. I'm Jaya Shivalsan Nair. I'm a faculty member at IIIT Bangalore, and I serve as the chair of the slate. We have with us Dr. Shyamlal, who is a faculty member at NIT Surathkal, NITK Surathkal, and he serves as the vice chair. We also have Mr. Gurudatta from MapMy India serving as the secretary, and Dr. Nagjyoti Kannan from ISRO serving as the treasurer. And we have a much larger members from IISc, IIIT Bangalore, NITK, MIT Bangalore, NIE Mysore. So it's a wide participation from several institutions. So the role of these EXICOM members who are also part of the student chapter, they along with the advisors and young professionals lead several initiatives of the chapter. Professor Dr. Shyam Lal has initiated 2 student chapters since the slate came into being. So we have a student chapter at NITK in 2021 and MIT Manipal in 2022. And we will continue creating a few more to engage the entire community. Our activities include summer, winter schools on technical topics such as machine learning and deep learning in GRSS, GRS, that is geoscience and remote sensing. Several talk series, including the Bhoo-Mandal talk series, hackathons, mapathons, student poster, paper presentations, conferences, and we also channel a whole bunch of call for projects, proposals, etc. from the IEEE-GRSS global section. We also participate very actively in conducting conferences. So currently MyGARS 2023 is going on, which is the machine intelligence in geoscience and remote sensing. It is going to happen in January, end of January in Hyderabad. So all the work is happening right now. The regional flagship conference in GARS 2023 is coming to Bangalore next year. So keep a watch for it. That will be in December 2023. And for all of this, we work with several other chapters in India. So the chapter in Gujarat section, Kerala section, Kolkata section. So all of them are quite active and we all work together to get these conferences going. The overarching goal of our chapter is truly diversity, equity, and inclusion. So we would like representation from different sectors, industry, government, academia, etc. And we would also like representation from different parts of Karnataka, north, south, east, west. And we would also like from different levels of professional expertise, like students, young professionals, senior members, etc. Right. With that, I'll now talk about the Bhoo-Mandal talk series. I'll also give a whole bunch of websites and information in the chat soon. I'll talk about the Bhoo-Mandal talk series now. This talk series is a public one and it started in July 2020. Its aim is to educate, enthuse, and inspire citizens about all aspects of science and engineering advances in Earth observations and remote sensing. Bhoo means earth and Mandal means sphere in Sanskrit. So hence these talks really touch upon various aspects of geoscience and remote sensing, including technology, say computer science, electrical engineering, etc., or be it society, policy, etc. So we cover almost all of them, and we get a variety of speakers from both genders and from across industry, academia, government sector, etc. So with that, I'll now pass on the stage to Dr. Shyamlal to introduce the speaker. So some housekeeping first. If you have questions, please feel free to ask in the chat. You can note, ask when the slide is ongoing, and we can also take the questions in between. Yeah, have a good time at the Bhoo-Mandal Talk series.
Thank you, Professor Jaya, madam. Let me introduce the speaker, today's speaker, Amruth Kiran. So Amruth Kiran is a senior associate, a part of Geospatial Lab at Indian Institute of Human Settlements, Bengaluru. His main area of expertise is building a spatial data platform and frameworks for big Earth observation data analysis, spatial data infrastructures, and a large-scale survey design. Amruth holds an undergraduate degree in computer science from BTU Bangalore and a postgraduate degree in remote sensing and GIS from Indian Institute of Remote Sensing, Dehradun, with this specialization in geoinformatics. Over the years at IIHS Bengaluru, he has developed various methods to centralize spatial data management, visualization, processing methodologies that enable researchers to quickly access spatial data at different scales. He is also part of faculty at IIHS Bengaluru, where he trains student and researcher in a spatial thinking, mapping, and the tools for remote sensing and GIS analysis. With this, I request Amruth to start his session. Over to you, Amruth.
Thank you, Professor Jaya. Thank you, Dr. Shyamlal, for the introduction, and also to the whole chapter, Bangalore chapter of IEEE-GRSS for having me here. I'll just start sharing my screen, and then I think we can slowly go over it. Yeah. So welcome. We at the Geospatial Lab at IIHS, over the years, we've been tinkering a lot with modern geospatial applications, modern geospatial frameworks. And we have come across a few of them, which we are fortunate enough to land as projects here at the Geospatial Lab. And given the support here at IIHS, we were able to take it much further than we were hoping to initially jump forward. And one of those specific projects is called as the India Data Cube project. And presenting here would be a small section of it, which is the foundational piece of our overarching project that deals a lot with spatial sampling methods and a lot of machine learning. But due to the scope of the presentation, I'm only restricting to the technology behind it, how we used cloud application and cloud services like the Amazon Web Services, and of course the Open Data Cube library to sort of build this large framework. And then how did the data cube in the lab sort of grow to more than something that we had expected it to be, not just a framework for processing data, but something more than that. So with that, we'll just quickly glance over them. With geospatial applications, we know that there is a lot of information out there. And that is one of the major themes coming into the Open Data Cube framework or the Data Cube framework, saying that how do we sort of store data? How do we, manage it and share it and things like that? So, coming across satellite images or IoT, social media, business intelligence, survey data, now high resolution drone data, we are expecting petabytes and over that over the coming years every single day. And having built extensible or scalable frameworks across computer science, connecting domains such as geoinformatics or remote sensing really helps to sort of validate and pull them together. But traditionally speaking, we know that there are 4 pillars of data management. One is, of course, data itself. We have then the metadata behind it. We have software and hardware. But what we have seen is that across all institutions, academic or non-academic industry, most of GIS professionals, most of the researchers, academicians tend to rely only on the data and metadata. If they can get their hands on this very well, I'm sure most of their projects will go well, and they don't really think too much about what can be done to sort of extend it a little bit further, because we know software to handle the data and metadata is purely a skill-based technique. And then anything below the software level, we are like, there's an IT department for that. Let's not really worry about it. But there comes a time when there is just an over amount of data that teams cannot handle, let alone specific IT teams or anybody that in general. But seeing the growth of all of this together, we hope to see that there should be an over-encompassing, a ring that sort of pulls in all of them together, that can be controlled centrally. It's just a reference to one of the old fictional books that I really love, Lord of the Rings, where we say that, one ring to join them all. And I've modified this a bit here, saying that with the power of those rings, we can bind them together. So from what you're seeing here is that the Open Data Queue framework has the potential to actually take data, metadata, software, and hardware all into a single shell and then scale it up as and when needed. So the overall pipeline that we see, very traditionally that we see, is that even here at the lab, what we do is that initially starts out with data creation, right? And this would mean either actually surveying the data yourself on the field, geotracing them on applications such as Google Earth Engine and other, Google Maps and things like that. OpenStreetMap, of course, is one of the largest data repositories, open data repositories out there. And then we sort of tinker with this and modify them and change them for specific needs and requirements. But then there comes a time also where data created at labs and institutions require a lot of updates, requires a lot of quality control and checking. This is a step that has to be very well maintained and has to be followed through very specifically, because any changes here that is not maintained or versioned very well can have a domino effect that can fall towards the analysis part of it. For example, if you're talking about satellite data, if the satellite data isn't processed to the right level of requirement, we can see that it actually affects the level of accuracy that can come a few steps later. Then, of course, we have the styling and symbologies, where we actually start to put in some visual aspects to make the data a little bit more clear, to make them discrete, to make them stand out. And then within the data management, when we look at large Earth observation data, vector or raster-based data, we see that a lot of it has to be indexed. And this is coming from a very computer science term. Index basically means a point of reference to the data and not the data itself. It's literally, it's like, an index page of a book. It says that this data is in this position. And, if you have to get this data, go to this place, right? So it's creating a very quick reference to the data. And we'll see why this is important in an open data cube system. And this is actually pretty common across most databases, if not all of them. If you see towards PostgreSQL, MySQL, and all of them, indexing is an important part of GIS databases, not only the regular non-GIS databases. Ingestion is a very specific term. In non-GIS databases, we talk about ingestion where we are actually transferring the data into the database. But when we talk about GIS databases, or here the Open Data Queue framework itself, GIS ingestion is a term that is usually for performance management or optimization. By that example, I mean, for example, changing the projection system on the fly. That is a process that can be carried out using ingestion, or maybe downsampling or upsampling resolutions within the database on the fly to a module that pulls in the data. That can be part of ingestion. Although a point to note here is that this is a data management pipeline. Ingestion is not a supported feature in the Open Data Queue framework anymore. That is a legacy feature that has been discontinued, and we'll talk about that in detail. Once we start ingestion and indexing, we see that cataloging comes into play. This is basically the actual first step of data management for a lot of folks who feel that categorizing the data is a step for databases, for data management, cataloging, and creating very specific metadata profiles or categories and names and nomenclature methods actually helps in the discovery and the exposure of the database or the exposure of each element within the database. And only once those elements are exposed in a very obvious fashion that researchers or developers, for instance, can consume, for example, plugins in QGIS that can pull in data from a database, only then can analysis actually be carried out. And once the analysis is done, we have obviously the visualizations. This could be anything online or offline, something that is very interactive. A lot of the elements that we see today in WebGIS plays a major role in this part of the data management pipeline. And the next two steps are something that we have seen over the years is quite important, but it isn't being followed as efficiently as we can. For example, outreach is something where we can actually have data portals that specify standardized data management techniques and data sets that, for example, have a DOI number attached to it that can be linked to papers and articles and other references, but they don't reach the audience that they have to consume. An initiative, I think the Google data platform has come out. So it's basically a Google search for data sets. If you could check online, and I think is a very a good step in the right direction for something that's very centralized, because a lot of us think of Google as a search engine, and it took them some time, I guess, to actually have a search engine for databases or data sets, for example. And then once outreach is done, action. I guess this is where it's on the fence. Action in the sense of actual implementation of the analysis and of all the work that has been done till now. It's a step that is definitely missing, at least in the Indian scenario. We do not have a straightforward method of actually building across data portals, or for example any projects with a dead timeline that says this has to have a workshop in it, you have to train folks in these things. It's slowly picking up pace, but it's definitely a step that has to be included by default in a project that has GIS, geospatial data within it. So this is sort of like the traditional platform or the traditional pipeline for a lot of this. And
So
behind,
Amruth,
sorry.
second, if
Yeah.
it's okay to, I just wanted to ask you, since there are a lot of students here, how do you do database search on Google? I'm just prompting whatever you have.
Sure. So there is actually a new portal that has come out. I think it's called as the Google Data Portal or Google Data Search.
Okay.
We can just search it out. I'm not sure of the exact URL.
Yeah, that's okay. So what is the search key that you give?
Yeah, so basically what that actually does is it's not a repository of data, so they don't store the data. They're an aggregator, for example, of various URLs and other databases. So what you're seeing that, for example, if you go on the portal and type in India shapefile or India national or international boundaries, it sort of pulls in all the available resources across the world where this keyword is part of a database that is part of a organization. Now, for example, if IIIT Bangalore or IIHS has India national boundaries or any other geospatial data format that is exposed to the Google data crawler, so they sort of have a crawler that goes across all of these resources. So we have to follow a specific guideline. It's in the developer documentation about how can you expose your data sets to the Google data portal. Once that is sort of followed, Google automatically sort of pulls in the data sets, and you're able to actually view them and then download them directly. So it's a standard procedure that the Google developer documentation has. It's quite interesting to see the different variations there.
Sure, Amruth. Chetan has helpfully given the link in the chat.
Yes,
the Google data crawler.
Yes, that's the one. Thank you, Chetan.
So you can carry on.
Yeah. So actually linking to the Google data crawler itself, how it does that is actually using metadata. Like for example, Yeah. So there are different metadata guidelines that are out there. I won't go into much detail about that, but metadata basically, of course, means, talking about the data, description about the data itself. And there are a lot of standards out there following from OGC, the Open Geospatial Consortium, or even from ISO itself. A few specific for Europe, such as Inspire, and then for the Americas, there is, I think, FGDC and many more. So the problem with all of that is since there are multiple standards out there, standardization itself is a question now. So behind all of this data, there are a few of these key data variables that I've just put on the slide here. And they can talk about projection and scale at different methods. They can talk about a lot of attribution when it changes hands from organization to organization, how these data sets and metadata are compatible across software systems or different tools and APIs. And are these data sets exposed to the internet, or for example, exposed to this Google data crawler that can actually pull in the data for users to find them. So all of this is something that the metadata or the data management pipeline is also missing. What we generally try to do, I guess, is use Google Drive and things like that to share data across a small group of people. But we've been experiencing or sort of experimenting with a lot of these techniques here at the Geospatial Lab, where we can build a public portal, for example, that can have access to a lot of the geospatial data that is being in the works within the lab, and also, for example, pulling in data sets from NASA or USGS, maybe ESA and all the other places as well. So exposure to these data sets or these databases are intrinsic within the metadata itself, and the Open Data Cube has a method to handle this, since it's built on top of something called as the GDAL library, the Geospatial Data Abstraction Library. So it's a very powerful API and set of libraries that can function, actually functions as the core of GIS and open source GIS right now. So just wanted to point that out, that metadata guidelines is something that also is quite intrinsic and important for a lot of applications. Now, actually diving in to the data cube itself, it's a very, it isn't a new concept. So we have been seeing data cube itself being talked about in computer science for quite a while. Since data lakes and data warehouses have been the trending term, I guess, recently because of cloud computing, but older organizations from the likes of IBM have been doing this for quite a while. And what they specifically say as a data cube is an ND array of values, or multi-dimensional. The N specifies it could be 1, 2, 3, as many as possible, and D is the multiple dimensions there. So under computer science, we see that it's also called as OLAP, or the online analytical processing. There are many other categories within that itself, but basically saying that you have a multi-dimensional cube, and across the cells in the cube, you can travel in multiple directions, X, Y, and Z, to fetch values in very simple terms. And these values are dependent on the different categories they fall under. Now, for example, in the image that you see there, we see that on the vertical line, we have the products 1, 2, 3, 4, and the other axis, we have the different quarters, right? And then different layers specify different regions, right? So this can be visualized in sort of a 3-dimensional way, that you drill across the cells. You can actually get values from each quarter across multiple regions and across multiple products, right? So you're doing a very I don't know if multivariate is the right term to use here, but some sort of technique where you can actually slice and dice a cube to get values. And that's the major concept behind the data cube. And that is what is also carried into something called as the geodata cube. Right. The main difference here, of course, is that this is specifically created to store and analyze spatial data. And the dimensions here, of course, are the spatial coordinate values. Space and time, and they can also contain something called as the sensor information or product types. So on the left side, the image on the left that you see there is a representation of a data cube of a certain region of the world with different themes across time. So the deeper that you go into the data cube, you're actually going into various time series or different timelines of the cell. And then across each of those single cells is one different product. So one could be, for example, the temperature of the African subcontinent region and the Europe region. The other could be the overall, the humidity or the temperature or evaporation and things like that. So each of them is a product, and then you can actually travel through time across all of these products and fetch values from that. Again, this is similar to the data cube, where you're slicing and dicing into the data cube and fetching values from each of those cells. On the right-hand side is an image pulled in from the Australian Geoscience data cube that sort of shows each one single cell. Basically, you see that there are Landsat scenes from different times and 4 different time periods, 10th June, 7th April, and so on. And then these bands or these image layers, scenes basically are stacked on top of each other. And then if your area of interest lies within one of those regions, you can actually drill down. So this operation is called as drilling down multiple time periods and then fetching a time series value from each of those layers. That's how this is sort of visualized in a very simple format. So the measure of these values are the data values associated with each dimension. So if you have multiple products here, for example, you can actually cut across products and get land cover information. You can get population density. You can actually run machine learning operations on this, because there's a lot of this is one of the foundational methods of tensor data as well. So a lot of opportunities to play with a geodata cube or a data cube in itself. And then an open data cube. I know there are a lot of terms being thrown around here. I'll hopefully be clear enough to make the difference between a data cube, a geodata cube, an open data cube, and then our India data cube. But the open data cube actually started out as a program in Australia under Geoscience Australia and the National Computational Infrastructure there, the NCI, and under the Australian Geoscience Data Cube was sort of developed. And the idea there was they were looking into sort of analyzing the whole of Landsat archive from 1985 till the present date for the whole continent. And you can imagine how many petabytes of data that is and how much of resource that would be required to run that at a hardware and a software level. So they did come out with an initial product called as the AGDC, which is sort of the precursor to the Open Data Cube. The AGDC was developed, and they have a few papers out there and actual demonstrated applications about running a continental-based analysis on Landsat archive for the whole of Australia. And then they sort of improved upon that as AGDC version 2. And the idea there was to now do a little bit more complex methods, jump into a little bit more detailed analysis and other computational methodologies. And it was also open sourced as the Open Data Cube. This is available online, of course, on the GitHub, on their website. They have excellent documentation for all of the processes that is described here. So on the small image that you see here, it's a very quick diagram sort of to say the different pillars of the Open Data Cube itself. So in a lot of native file systems, that is a traditional data management pipeline that I was talking about, you have just data stored in different folders, right? We have project data, and within that we have vector and raster, and then different processing levels and different resolutions, different projections as just normal files in your Windows or Linux machines. You can use that obviously as the raw data to now plug it into your Open Data Cube, or you can also have something called as an S3. S3 is a service provided by AWS. AWS is Amazon Web Services, a cloud provider. S3 is stands for, I think, simple, one of those names. So basically, it's a S3 bucket. You can actually dump a lot of file-based data onto a cloud. In very simple terms. So what it does is it sort of replicates how your file system would be, except that it is a little bit more scalable on the cloud, actually much more scalable on the cloud. So it's easier for human-to-human interaction. So you can actually see the files within folders online, and it's very relatable for someone to actually look at these images online and click and download them and link them. There are obviously much more efficient methods to store data on cloud, which we will be seeing when we jump into the actual the flowchart of it. But basically saying that the data, wherever it's stored, it can be plugged into the Open Data Cube library. and then it is indexed onto a PostgreSQL database. So this index, what it does here is it creates a point of reference to wherever the data is stored on the native file system, or if it is stored online or on the cloud. Right? It could be on AWS, it could be on Azure, Microsoft Azure, it could be on the Google Cloud Platform, it could be on Droplets in any of these cloud platforms. And then the infrastructure then is sort of linked to the different applications that can use this data now. It could be the very famous Jupyter Notebook interactions, or other spatial web services like running geo servers or other open web services from this data, and of course APIs to directly connect to developers running raw Python scripts or R-based programs. So that's the basic gist of Open Data Cube. Now we'll just actually see how the India Data Cube sort of came into play. First, I'd like to go over this, saying that the India Data Cube, the name of the actual project is called as the sort of understanding the Earth observation data with census and sample surveys to estimate development indicators for India. That's the sort of the actual project headline. This is a project sponsored by the Group on Earth Observations GEO and Amazon Web Services Cloud Credits Program. So if you're interested in actually gaining cloud credits for a project of yours, basically getting funded to run cloud computations online on AWS or Azure, you can actually look into these cloud credit programs that come out very often. And they accept proposals based on, it's actually detailed into the theme of what they are providing right now. So, once you do put in your proposals and if there is a progress onto that, you will be awarded some amount of cloud credits that can be added to an account, and you can run your high level processing all completely online till the credit expires. So we were given a good amount on AWS to run a lot of this. And over the last couple of years, we were able to actually bring about the data cube within this, right? So the idea here was that we'll start to organize, disseminate, process, and then visualize a lot of big Earth observation data, and then building the data cube. Technically speaking, could be the first of its kind, because there are other implementation that officially at the Indian Institute of Remote Sensing in Dehradun, they had carried out a preliminary understanding of the data cube some time back, but that was at a state level, if I'm not wrong. And the difference here is that with the India Data Cube, we try to pull in a lot of satellite imagery and any other sort of data that can be pulled in, for example, sample data, survey samples data and census data at a national level. Because it is all on the cloud, processing is not a bottleneck. So we were able to pull in data sets from the likes of Landsat and Sentinel, MODIS, Cartosat, and a few other proprietary data that we had purchased, and a lot of environmental derivatives from them, environmental variables that can be used for modeling, for example. And then over the period of the project, we also created a lot of machine learning products that are specific to the project. We were also able to run or implement that as a product within the data cube that others can also use. Like I said before, the IDC is developed using the Open Data Cube library completely in Python. And then we used very similar deployment methods on AWS based on our conversations with the Open Data Cube team, quite informally over their communication channels some time back before we actually started it out. So one major question that this basically asks us is that a lot of organizations or folks coming into research, for example, are not sure if cloud computing is a method or not, and there's a lot of hesitation towards that. And I think the first one that a lot of people have spoken about is the legality between running cloud computing on specific remote sensing or GIS data, and this is very specific to GIS and remote sensing, obviously. So data sovereignty basically means the security aspects of the data, the border issues that the country is facing, putting data set such as this out in the open, is it going to be a problem or not? Can data set specific to a project that is in Mumbai, can it be hosted on a server in Switzerland, for example, or the US? These legal questions are at a very deep-rooted level at an institution. So, and that is where a lot of these things fall. So I think once that is cleared up, I believe that opens up a lot of opportunities to actually go into the cloud. And then, of course, the whole business aspect of it is the cost. Handling cloud resources it requires a lot of skill, but also a lot of financial support. Given the right amount of personnel and training, this could actually turn out to be much cheaper than having a non-cloud or on-premises server-based systems. And then after that, or directly linked to that, is the actual skill-based practice. Cloud computing certificates and all of these things are available, but actually doing it hands-on with over some time is the only way to sort of build up experience in using a lot of these tools, like mostly everything else in life, I guess. But we've seen that running all of these processes on for free for some time sort of helps build the motivation for a lot of researchers to jump into the cloud to do a lot of these things. And AWS and Microsoft Azure, Google Cloud, they offer a lot of these free programs or free tiers for students and everybody else to actually get a hands-on experience on the cloud. And it's available for, I think, 12 months for a new account on AWS for sure. So you should definitely jump into it without having to worry about, being billed and any other problems arising from that. So thankfully for us, the three pillars here that you see were sort of solved, and we were able to get into the project quite quickly once the credits rolled in. And once the credits did roll in, our main idea was to now put in all of these data sets together. And this took quite some time because we had to narrow down what sort of satellite images do we need? Do we need only a raster? Do we need other vector sources? Do we need tabular data or not? Do we have to georeference PDF files and scan, maps and things like that? So narrowing down that roadmap is quite important. So gathering a lot of these data sources is obviously the first stage of building any sort of data repository. And once that goes in motion, we see that we actually start to set up the Open Data Cube. And this is pretty straightforward. I think the documentation is excellent for a completely community-based effort. And this sort of deployment is available on both Windows and Linux-based systems. It is completely scalable on the cloud as well. Of course, that's one of the reasons we're using it on AWS. It has been tried and tested. So this went ahead pretty well in this stage, I can say. Then we also have actually setting up these Jupyter notebooks or Jupyter Lab setup. For those of you who don't know of Jupyter notebooks or lab, it's basically a very interactive method to run softwares or to run Python scripts or R-based scripts on a browser. So you basically have different cells that you can put in your commands in, and then you can actually see each line of code as it is running. It's a very step-by-step, very beginner-friendly method, and one of the most preferred method to actually share code or share implementations of code online. And the Open Data Cube community has a lot of the Jupyter notebook samples available on their GitHub, for example, that showcases how they did, for example, the setting up of the Open Data Cube on AWS. How did we load Sentinel data or Landsat data into the Open Data Cube and things like that. So it's a very good way to share knowledge when it comes to programming interactively, I guess, the Jupyter services. Then speaking specifically about the management part, that is on AWS. I see a hand is raised. Yeah, Pratiksha?
Yeah, hi, Amruth.
Yeah.
So this Amazon service mentioned, is it the same as Amazon SageMaker? Because I recently read that they've included geothermal capabilities as well.
Yeah. So yeah, thank you for the question. So Amazon SageMaker is one of the services that fall under Amazon Web Services. So Amazon Web Services is the overall the main person, I guess. There are like 60 or 70 different products under AWS. And Amazon SageMaker is a very specific service that caters to machine learning applications on AWS. And I think it's currently under preview. I'm not sure if it's open to the public as of yet, but it says that a good amount of GPU-based training for machine learning applications are quite easy. You can use, like, if you've used QGIS or ArcGIS model builders for interactively running algorithms, SageMaker is trying to sort of replicate that in some senses. So it's in a preview mode, so we don't really have access to it as of yet. But yeah, it's one of the products or one of the services offered by AWS. Yes. Yeah.
Okay, thank you.
Okay, thanks. Yeah, so in stage 4, we see that it's user management, and this I mean about AWS specifically for or for any cloud computing interface. The reason I put this in is because, like I said in the previous slide, that this requires some amount of administration or some amount of skill required to understand the different services. There are a ton of AWS services, and knowing which goes where is a complete course on its own. So learning them and then assigning users to these services, and giving them enough permissions not to do, for example, running too many processes on a single virtual machine can bump up the prices a bit and things like that. So understanding all of that is an important step, and that's something that we actually took up without any external help and learning it on our own on AWS. And once the management part and all the setup is over, we actually hand over the virtual machines, the processing steps, whatever we have done so far, to the users themselves. And by user, I mean our researchers here at the Geospatial Lab. So they're given access or limited access, I can say, to do whatever analysis that they actually want to do, and for at least under the project that we're working on, right? And then once that stage is done, okay, this is a little bit deeper dive. I guess I could have come here, but yeah, I just wanted to go through one specific slide here, the one on the bottom. If you see here, I say the last two: estimating cost and volume, and copy and sync to IDC region. So one specific thing that we took up in stage 1 was to actually estimate how much this would cost us. So since this is all on AWS, there are different calculators that you can use to say that, okay, in a month, I'm going to be experiencing around $200 or $300 worth of usage. And since this is built on the credit system, I actually don't have to pay for it, but it gets debited from the overall credit that we have accumulated. For example, if you have a credit of $50,000 and you're estimating a use of $200 to $300 every month, that amount will be debited from the 50,000 that you have, right? And so that goes on and on. So you actually do this sort of estimation, and then a lot of other methods to sort of establish a trust that you won't overestimate, or you won't run out of credits in a while or two. And then one important step in the bottom that if you see there is actually to get data sets from some place or any place that provides it in an open registry. And one of the ones that we found was something called as a registry of open data on AWS. So this is a complete repository of all open data that is currently available. You can actually check it online if you're on your laptop right now, and you can actually see that a lot of Landsat data, Sentinel data, a lot of very specific project level data has been put out in the open. And you just need like an account online, and you can directly download a lot of these satellite images and a lot of other derivative products to your systems directly. And you don't, one of the best part about this is that you don't have to use the, for example, if you're taking Landsat data, you don't have to use the USGS Earth Explorer or anything of that kind to get the Landsat tiles. You can directly download with using just a couple of lines of code, whatever that you want to take. And then one other aspect about cloud computing very specifically is that since this registry of open data is in the United States, specifically in Oregon, we moved a good chunk of data, Landsat, Sentinel, and MODIS, if I'm not wrong, to India. Moved in the sense made a copy. The reason for this was that since a lot of processing is time dependent and time is money here, because the more amount of time you spend on a virtual machine, the more it bills you. So the sooner it can actually run processes and copy data and write data and offload the data, the sooner we can actually shut down the virtual machines costing us money here. So what we did was we took the data from the United States, Oregon, and then we made a copy of it into the Mumbai region where AWS has its data centers. And then we built our virtual machines and open data cube libraries within that region. Right. So this saved us a lot of time. Obviously, storing this data, whatever we copied from the major data center in the United States, will cost us a bit, but it is still less considering how much we would spend if we were to now process it across continents, for example. So that's the bottom part, the copy and sync to the IDC region. So we just created a lot of bash scripts that what it does, it basically scans if there is a new scene available on Landsat of this, or if this region of India has a new scene coming up or has it already come up. And if that does not exist in our database, we create a copy of it. If it exists or if it does not exist, it tries to sync it in real time as much as possible. So this sort of maintains a versioning system that, okay, whatever data comes through to the actual data centers there can also be reflected on our end as well, right? And then the stages 2 and 3. Just going in detail here, saying that we actually created these virtual machines on the Mumbai data center, and we created a couple of them that are used specifically for indexing the data. So like I said before, indexing is a point of reference to the data, not the data itself. So this machine sort of runs all the indexing scripts that are required as a mandatory step in the data cube documentation. If you read that, it creates a lot of these indexes within the Open Data Cube's PostgreSQL database, right? So it can do this, or we can do the second step, that is actually offloading the database entirely to a third-party system. And what we did was we used the index node to offload all the data and index it into a more scalable system called as the AWS RDB, or the Relational Database Services, RDS. What this does is basically we are now not dependent on having the database within one or two specific Open Data Cube index nodes. What we have now is that there are multiple ways to now get the data because they're all centralized. Now, a centralized AWS RDB or RDS service, now once that is deployed, it is much more safer, because now we know that it can't be deleted by mistake, or you can connect multiple people to the same database and run it instead of connecting multiple people to an index node. Index node is just a very small machine just for copying and indexing data. But the AWS RDS is a much more powerful and scalable service that can store a lot of GIS, or specifically here the Landsat or satellite imagery data. And then what we did was, once the main database was set up, we actually created the compute nodes. The compute node here is the actual processing part of it, where our researchers here use these nodes to run any CPU or GPU intensive applications. It could be training of data sets, it could be a lot of large scale mosaicing operations and things like that. So this is where the actual heavy lifting happens. So you can imagine machines with, for example, starting out at the minimum of 32 GB of memory and running all the way up till 600 to 800 GB of memory. We have touched upon almost 800 GB of memory for a few of our processes as well. And then this is because we have transferred over 55 terabytes of Landsat 5 and Landsat 8 data for very specific time periods of the project. I think it was 2001, 11, and then 20, following the census years, whichever census years was available at least. And then over 10 terabytes of Sentinel and a few other terabytes of other derivative products as well. So now running all of these terabytes worth of satellite imagery, you can understand the amount of resources it needs. So upping the RAM or upping the memory and upping the GPUs sort of helped us reach a considerable step, if not a full method at least. And then since this is also a proper compute node, researchers can use this for Jupyter services. They can use it for APIs, or it can also be like a test bed where they're just testing out their code, just seeing what happens, just understanding what the Open Data Cube is. And then finally, obviously, a lot of management happens. We can't have somebody spending $1,000 or $2,000 in a day or across a month even. So try to limit access, learning what has to be updated, what has to be optimized, what services has to be changed, and things like that. And then finally, one of the reasons, the little bit of concern is again the management of all of this. A lot of people have come across saying that, your AWS accounts has been hacked. I've lost access to it. What do I do now? I'm being billed lakhs of rupees now. So these issues have come across, and there is an extremely supportive AWS team out there that can help you in the training part of it, the documentation part of it. And then we here over time, we have learned all of this from honest mistakes as well, and to sort of teach or train our own researchers here into collaborative usage of AWS. And then over time monitor and then change things as and when required. And of course, like any other administrative task, you have backups and maintenance and updates. So this is a overall or a very simplified diagram of the whole architecture that we followed. If you see the smaller box at the top that says Oregon, so that is the S3 bucket or the data repository for the open data, the open registry for open geospatial data there. And then we did a request and pull method using a simple bash script and pulled it into something called as our index node. If you see the Docker icons there, if people are not familiar with Docker, it is a containerization service, basically saying that if you were to now deploy an application on a very specific set of software and hardware requirements, you can now package all of this into something called as a Docker container. It's like an image that can be transferred over to another cloud provider or another machine, regardless of the operating system, regardless of the hardware, and it will work as expected. So it is packaging all the required libraries, all the required APIs and other things that need an application to run on. It could be data sets, and specifically talking about GIS, it could be all the GITA libraries within it. It could have GeoServer within it, anything of that kind. So you can package it all neatly and then just pass it across to anybody who needs the same application that you are running, and it will immediately deploy using the Docker services. It is a little intensive on the machine, but it gets the work done if you know how to optimize it a bit and run with it. So using this index node, if you see, we did a copy and sync command that transfers or copies all the requests that we need for the data onto Mumbai region, the larger box inside that shows Mumbai. And then we use that to index onto a central database or the AWS RDS system. Right. And then since this is in real time, people using the compute nodes on the bottom right can use as many applications they want, connect to multiple schemas on the database, multiple users across these compute nodes can connect to the same database. So we see a lot of actual benefits from centralizing the data on this end. And like I said, again, this is also Dockerized or containerized, a better word here, that can be replicated across as many users as possible. Yeah, so this is our major or at least a simplified method of showcasing the architecture. So what we've learned so far is that one major accomplishment, I guess, what we have been trying to do is that a lot of these tasks take time. And one of the major things that we are trying to improve upon is that using something called as parallel processing and Dask. Dask is I think a Python library for parallel processing. So we've improved upon a few aspects that we were struggling with initially before. One of them obviously is the copy and sync command. So the copy and sync command is a very unilateral approach where it follows file by file. And we have transferred over, I think, 100,000 Landsat tiles, and each tile is one file. So you can see how long it would take to actually transfer one tile at a time. That is 100,000 requests at a time. So 100,000 requests one after the other in a serial order. So that would obviously take a lot of time. So what we did was we tried to parallelize that in a different method, and we were able to do that on a single index node itself. And what that does is creates multiple threads within the CPU to sort of run these copy and sync commands. So now you're running maybe 5 or 10 different requests at the same time, and then pulling the 5 or 10 different tiles at the same time. So that sped up our process quite considerably. Then, of course, using a Dask library, you can again, if there are anybody out there who are interested in parallel processing for remote sensing applications, especially under the X-array type of data type, it's called as Dask, D-A-S-K. You can use this library to do a lot of parallel processing. So it does a lot of its own heavy lifting. So I would really recommend all of you to jump into that. If you're looking into actually running high workloads on cloud or high performance computing machines and things like that. So that's one of our highlights, I guess, in building this foundational package. One is again the centralized database, although now I think the Open Data Cube documentation has been updated, and I'm sure there are much better ways to now actually centralize database, but something that actually worked for us, it worked out really well. Now having a separate database has its own benefits now, so we can actually shut down a lot of these index nodes, we can shut down a lot of these compute nodes and not worry about losing the data, which is a prime component on running anything on the cloud, is that if you're not using your machines, you have to shut it down because you're being billed for every hour it is on. So now shutting down these compute nodes when it's not being used actually saves us a lot of money. So, and we don't lose the data now because we know it is completely stored in a different kind of service that can be pulled up anytime for us to use. And then again, the containerization topic that we talked about, having them all packaged into a very scalable method. So this Open Data Cube implementation of ours now can be taken and put up on Microsoft Azure. It can be taken, put it up on Google Cloud, or it can be also deployed on the local servers that you have, or anything for that matter. So there is not any dependence on the software or hardware part of it because of the whole aspect of containerizing most of these applications. And it's a very standard practice now. I think in software development, we see most of these applications either put this out as one of their major product releases, which is quite good. And most of it is available for anybody to jump into and follow, and very easy to actually do. And then actually running APIs. So one thing that we have seen is that having this as an open web service is also quite useful. We can actually have a lot of this being streamlined into QGIS, for example. You don't have to run it on a normal Python script or Jupyter notebook or anything that kind. You can use this for running it on GeoServer and even the GIS extension of PostgreSQL, that is the PostGIS extension. And then this can be used for a lot of simultaneous Dask-based loading and processing techniques. So one idea was that we start that out as, for example, the highlights that we have seen here, right? We need something for processing data, right? We are storing terabytes of data, and that was the initial implementation of the data cube, I can say. But over time, what you're seeing that this can be used quite well for actual management of spatial data itself, because the Open Data Cube comes in a very good versioning system. You can have multiple products, and by products I mean, for example, the Landsat series specific to level 1, level 2, Sentinels at very different resolutions, for example, resolutions that have been changed by researchers or developers, for example. So all of this can be actually maintained very well within the data cube itself. And then obviously the metadata behind all of this can also be controlled quite well. So people or administrators of the data cube can have access to this and update these products, delete them whenever they want. Give specific user permissions that, this kind of data set should not be accessed by this kind of user or things like that, right? So the things that we talked about, having a multi-user or a multi-data management framework previously, the Open Data Cube can actually go into that. Maybe not as fully fledged as we would like, but there is definitely a scope for all of that, and that is something that we recognize, and that is something that we would actually try to take it up. And most knowingly, because it actually serves multiple purposes, right? It's definitely like hitting multiple birds with one stone sort of a thing. So and then finally we have our test bed. So this is just our playground, you can say, like a sandbox environment where folks have access to the data. Now we don't need to tell somebody to give us a link to Landsat data from so and so year. They just have a couple of commands. They can go into the data cube, pull that out, and then run whatever they want, either on their own laptops, on their workstations, on the cloud, anywhere. They can use that to, even run GeoServer applications where you can stream the data onto a WebGIS portal, for example, and then use that as a public-facing entity for showcasing products and things like that. That is something that the Open Data Cube community, specifically the Digital Earth Australia and Digital Earth Africa, have been doing quite well, and that is something that we at IIHS are also trying to come across sometime. And how it sort of plugs in the Open Data Cube, how it plugs into our overall ecosystem at the lab here, is that at the bottom you see the three larger squares that are our different platforms. We can say one is the discovery of data, one is the visualization of data, one is the processing of data. So what we've talked about is the bottom part, where the processing of data can be done quite quickly. So this plugs in very well with our existing infrastructure and the evolution of whatever infrastructure that we currently have in terms of hardware and software. So there are other tools out here. I'm sure these slides will be shared later on. All of you can sort of dive into them and see each of these tools in detail. All of them are open source, of course, and they can be found with extensive community support and documentation. Yeah. And then, yeah, I think the important part is the actual learning. So other than cost being one thing, which I'll actually come to that, we've seen that, actually keeping track a lot is difficult. There are so many updates in an open source community that we see here, especially on a framework or on a topic of interest that is so in use. A lot of changes happening very, very quickly over months, over weeks, and keeping track of all of that, their changes, how does it affect us? Will one of their changes completely derail our existing infrastructure or not? Or can we do something better? Or maybe their latest update is much better than what we have, things like that. So these kind of changes actually is a little hectic to keep track of, but I guess it deals with a lot of open source community, and that's just how it is, I guess. And then of course the angle of cost. Like I said, we have made honest mistakes in the initial parts of this project, where we have been billed quite a substantial amount of money, and then of course after some emails and after some community help and a lot of support from the AWS team, we were able to rectify the mistake. And it's something that we take quite seriously when we are dealing with cloud. Obviously, not everything is free, and understanding each service very deeply is quite important before we start out on any large-scale data management practice or any large-scale spatial data processing methodologies. And then something that we definitely should have done much earlier is understanding that we don't need terabytes of data, because obviously we know with satellite imagery a lot of them is cloud covered, right? So we need to plug in algorithms to remove cloud cover before they sort of transfer over to our processing compute nodes. Have methodologies in place that can take care of processing at different levels. Do we need raw data, for example, or do we just keep the final L3 process data? Do we need very detailed metadata that can actually take up a lot of indexing operations? Do we need that or not? If it's data created very specifically for a project, that has to be cleaned, that has to be quality checked, has to be maintained well. All of this has to be followed before it can be plugged into a data cube, because again, data cube is it's a framework. It does its thing, but your output is only good as an input. So if you have a lot of data, make sure that things are clear on what sort of data is actually required, what is not required. Spending a lot of time, spending a lot of money in maintaining all of this. Then again, a well-defined roadmap. This one is quite surprising, because this is a very overwhelming software or a library, I can say. The Open Data Cube is quite immense, and its usage now is across the world. We have Open Data Cube for Switzerland, we have one for Australia, Africa, I think one for Brazil, Colombia, if I'm not wrong, and a lot of others. And now one initially started out in Dehradun and then now here in Bangalore. So we are scaling up, of course, we're going much higher and higher. And what are the possibilities for this is quite big, because we can either stick to the data cube being just a simple platform for processing, or like we try to experiment experience that we try to sort of go behind is sort of a whole data management pipeline. So finding out what your use case is, I think, is a little bit more important than actually running them on the cloud or not. You can actually have the Open Data Cube completely on the servers, on your own machines, in your own institutions. You don't even have to go to the cloud. So understanding what roadmap you have to take initially, I think, would be the first step that you can do. We were quite fortunate with the workings of AWS and the support that we got. So I guess understanding that, maybe the clarity behind that is a little bit of a concern for us. But I think over time we have used that for our own potential and taken it much further than we could have. Then, of course, something very personal is that practices in modern GIS or in modern computing, software engineering for that matter, something that evolves very quickly over time. And then, as we see with open source community, there's a lot of changes that happens, and you having the skills, or you having a team of folks who are skilled enough to keep up with that is also quite important. So the project is as good as its team. So having improving as many skill-based protocols and things like that as soon as possible is the best way to go forward. Of course, these are just a few of the learnings that I wanted to highlight. There are a few personal ones as well, I guess. But yeah, and in the future, what we would like to do is that there's a lot. And for those on the first point here is called as a geomedian at scale. So basically, a geomedian is a mosaic or what you can say, the best pixel method of creating satellite imagery mosaics. Basically, you have a kernel, and the kernel travels across each of those cells, trying to find which pixel sort of fits the best in a very simplified method. So geomedian works quite good at all scales. But the problem what we faced was we were trying to support an analysis using or for machine learning applications, and geomedians, or at least from our experience, we were not able to produce a very good quality geomedian for applications that require a large scale mosaic, for example, right? So that is something that we are now experimenting on, trying to see what sort of changes or optimizations we need in our code to now have a very good high level analysis ready data for machine learning applications at a national scale. So few of these changes have come across, and we are trying to put them out in the open as soon as possible, and we are in the process of doing that. And the other aspect is that this eventually will be a service, basically saying that this is going to be some sort of a portal, sort of an implementation where folks can have access to the compute nodes, or can have access to the sandbox that we have for them to sort of try out the different data sets, do a simple remote sensing calculations and things like that, visualizations, and then use that as a platform for workshops. Eventually lead up to the final slide that I talked about action in the data management pipeline. So using this as a service to actually put out a message for whatever applications or themes that folks can come out with. And then there has been a latest addition for those who don't know about the spatial temporal asset catalog, STAC or STAC. It's more of like a standardized method of spatial or satellite images for the web. And it's a very high level method, or at least the way I'm saying it, you can actually stream satellite data quite fast in a very simple method to say it over the web using the STAC protocol. That's one thing. Second thing is that it's a standardized method of exposing a lot of metadata over the internet so that actual people who need the data can find it. So it's a very different method of exposing spatial data sets online as well. And now I think the latest release of the Open Data Cube has support for the STAC implementation. That this is something that we have not done. So this is something that we'd like to take up as well, because a lot of movement we are seeing now into the STAC method of spatial data exposure and consumption. So like I said before, you don't need to go to USGS Earth Explorer and then download tile by tile. You don't have to do anything of that anymore. You can actually use these interactive portals to stream the data directly onto your QGIS or ArcGIS environments, or Python, or things like that. So that is something that we would like to do as well, which links directly into the IDC as a service initiative. And of course, completely following the open source directory is that since the IDC is built on the ODC, the Open Data Cube, it would not be right to not go into the same route as they have. We would love to completely go open source into all the collaboration, into all the implementations that we have across the board, both at a software, hardware level, and all the other models that we've come up with. So eventually, we are still tweaking this a bit. We're trying to, put out a lot of these articles out there, a lot of technical white papers out there, trying to push a lot of these things out, to have a lot of collaborations come in, and then actually put this out as a GitHub account, for example, and so that folks who are interested in the project, something similar, maybe at an Indian context, maybe can replicate at their end. And then, like we said about the geomedian part of it, the machine learning centric is still something that we're trying to improve. Of course, machine learning and AI and remote sensing is a huge domain on its own, and it's something that I'm not an expert in, so I won't dive too deep into what it can do for us. But it's something that we would like to obviously cater as well, because we have a few machine learning developers here at the Geospatial Lab. So something that we can provide to them as well is a definite a plus point for us, I can say. Yeah. This is a snippet of our team. Of course, the whole India Data Cube team, you see the whole box over there, and we had complete support from Krishna Chandran, Teja, Suraj, Pratyush, and Krishna to sort of actually build this up. And a small open data cube with me, Reshma and Shubham. So we've been going through quite a bit over the last 3 years, I guess. 2-3 years have crossed since we have started this, and yeah, we hope to put a lot of these things out eventually. Come across many obstacles either on the data side or the processing side. Open sourcing it would definitely be a plus point. But yes, I think that should be it to sort of close up, hopefully on time. And I think we have time for questions as well, if there are any. If you'd like any sort of clarifications on any of the other slides, you can please let me know. I would be more than happy to go there. But yeah, thank you so much.
Thank you, Amruth. Participant, you can ask a question from the speaker. You can unmute yourself.
Yeah. Hello. It was a great presentation, Amruth. Thank you for having it. We got to know a lot. I have a few questions which I would like to know. The first question I would like to ask is, what was the time period you considered for building the IDC? Right?
A lot of the so the timeline, in the sense you mean the setting up, the whole aspect of that, or what do you mean specifically on the timeline?
I mean, what duration you considered for, like, we have the data from the Landsat from
Okay.
Sentinel,
Yeah.
the years, I mean.
Understood. Yeah, so there are two things. So we had very specific project requirements separately for what was required as a method of output itself. That said, that we needed time series data, for example, for all the sensors years. And whatever sensors years were possible, we picked them as a definite requirement of getting data. That is definitely there, right? But other than that as well, what we noticed was that just getting a few sensors years does not utilize the data cube framework very well, right? The whole idea of that, you can actually do it without a data cube as well, right? So the idea was that if you can have more time layers between those sensors years, and since more data for training is always a good thing, and that was suggested by our machine learning developers here as well, that we try to put in as many tiles or as many time layers between each available Landsat or Sentinel scene as possible, whichever was available and whichever were cloud free and sort of fell under the right amount of processing levels that they were looking for. So technically we had around 15 to 20 years, I can say, small gaps in between, not directly 15 years or 20 years directly, small gaps in between, whatever is possible. Ideally, we had to fill it up completely from 1985, whatever Landsat could give us. But that would obviously mean there's a lot of resource hungriness in storing the data and running it, and that would cost us much more. So we finally narrowed down to only the census regions and census time periods and worked only with that. But again, the framework is for something larger.
Okay, thank you.
Yeah.
Any other participant? You can go ahead.
So can I ask a few
Yeah.
questions?
Yeah, please.
Yes, yes, please, Raisa.
Thank you, sir. Hi, Amrit. It was nice presentation. I also started learning something new,
Thank
data
you.
cube and all. It's nice to hear from you. And I have few queries. I started learning Google Earth Engine. Is it something we can relate to Google Earth Engine, because that is also cloud-based platform and it is completely free of cost? Okay, that is my first question. I missed. I think first 10 minutes I missed it. So I need to go through that again. Now, the second question is, when it comes to heterogeneous data, not only the raster data, it can be any kind of a spatial data, it can be CSV shape, any kind of. So how to do a spatial query with a heterogeneous kind of data, and how to handle these kind of problem? Like, is there any documentation they will give how to handle this particular kind of spatial data? And for at least for researchers, I feel that India Data Cube should support, give it for a free of cost, at least for researchers. So that will be a motivation for us to start working on these kind of new data cube and all. Another one more problem what we are facing when we were doing batch processing. So when we want to do a steady area for a specific vector layer, we want to clip it for the entire year period or even the Landsat period, we have to go through one by one, right? Every data selection, we have to filter it and we have to clip it. And that is only for Landsat. At least we can automate the process. When you look for a different kinds of data, it can be Sentinel or any MODIs or any kind of data set, how to do a batch processing for the different data sources for a particular area within a short period of time. Is it possible to do by using data cube? Like that, few more question. I think I'm taking your time. So maybe in future also we can connect. Anyway, we all are in. Yeah.
Sure. Yeah. So I'll go over. Yeah, please. I'll go over some of the questions that you asked. So I think the first question about Google Earth Engine and Open Data Cube, I think this is something that has been asked since I think the development of the Open Data Cube. So there are a lot of folks in the community who have strong opinions on this. And I think there's also a blog article somewhere out there describing the difference between the both of them. I think the most important point for us, specifically for our project, what we felt was that proprietary data, specifically following the legal concerns of the state, if you know the rules of NRSC and things like that, you are not supposed to put proprietary data on the cloud, right? And you can't transfer it across machines and things like that. And if you want to utilize the Google Earth Engine compute completely for running very specific models or very specific processing for the data that you bought, you cannot do it, right? You cannot put that data technically or legally. I'm not sure if technically that's possible, but legally for sure you're not supposed to do that. So that is a major concern arising out of using Google Earth Engine with data that you have procured or, for example, that you have created. That is there. And coming to the technicality of it, there is the Open Data Cube is completely it is different, but it is also what can I say, motivated by the Earth Engine's infrastructure. So I think the author is Neil Gorelik. One of his papers on Google Earth Engine when it came out is one of the actual foundations on how the Open Data Cube is built. You have something called as the RASDAMAN, RASDAMAN. That is also a type of data cube used highly for scientific computing in, for example, weather forecasting and all of that. Peter Baumann, I think, is one of the authors who had come up with that. There are a lot of these data cube initiatives. So they're all, they can be called data cube in some sense, because right now there was a recent workshop held sometime back by the OGC trying to define what a geospatial data cube is. It's out there on, I can share all the links later as well. But they're trying to define what a geospatial data cube is, and all of these different players from across Earth Engine, Open Data Cube, RASDAM, and all of these folks try to come to a centric definition of what an Open Data Cube can be, and if their product actually falls underneath that. So I can say it is a motivation behind it, from at least from what I have seen. But if you do have questions like this, there is an Open Data Cube Slack channel that you can actually join, and all the developers, the core developers of the Open Data Cube, are available there for conversations, and they personally helped us out quite a lot as well. So I think these specific questions can definitely be put out to them as well, the Open Data Cube Slack. The second thing is the heterogeneity of data. So what we have seen is that since vector data actually cannot be handled on the Open Data Cube because it is not it is specifically meant for tiling of raster data or processing of raster data itself. So something that we had considered was actually trying to rasterize a lot of vector data. Right, it may not be accurate because obviously you're losing information when you actually rasterize from the vector data, but some efforts have been tried into that to find multiple different type of data sources, for example, to be pulled in or across multiple formats. But the data sources can definitely be pulled in. If you have Sentinel or Modis or anything of that kind, they are sort of intercomplementary to each other within the data cube. They are all standardized to the same metadata profile or anything of that kind within the data cube. Outside, they may be different, but once they're actually indexed into it, they're all the same. They're all within the PostgreSQL database, so they act the same way that you can actually use them to. So vector data, I think, as of now, has not been implemented and may not be part of their scope as well, because that does not require as much resources, to implement, I guess, and some of the reasons could be that. Vector data is definitely not something that we have tried to put into the data cube as well. So in that scenario, what we just do is that we transfer all the vector data or any other heterogeneous data onto the compute nodes that we have and not on the Open Data Cube. Since we have scalability on the compute nodes, we can run parallel processing on the vector data itself directly. So we don't need to put the vector data in the Open Data Cube. We just put it on the machine that runs the Jupyter notebook or the machine that runs the APIs, anything of that kind. Open Data Cube is just storing the different parcels of data very well and putting out at different time series and drilling them down and things like that. So we just circumnavigated that and went directly to the machine for vector data, I can say. The batch processing part, can you clarify that a bit? The batch processing that you asked about?
Yeah, suppose we have a lot of data set from the different sources. It can be a simple example, Landsat, Sentinel, Modis, 3 data sources.
Yeah.
But the study area is Bangalore region, like one study area on one layer. But we want to do it for a whole, like 1970s to till now. So then we have to clip our study area for a specific location. And what normal traditional way is, we have to look for the data availability, download it, clip it, or even Google Earth Engine also will be giving at least the availability of data, and we can just single line of code, we can clip it. But is there any way of batch processing? We are just giving the shapefile and the set of data sources what we want to do it, and give it in the form of a simple clipped versions of with whole years. Is it possible to do it?
So that's actually, if you remember one of the slides, I talked about the layers being stacked. I'm not sure if you were there in the initial set of slides. So it basically says that within the data cube itself, you have the different layers of data lying underneath each other because of the different time periods they are in. And an operation called as drill down can be used to actually drill down to the specific region of interest and go across time. So each layer is a time period, and then you're drilling down across across your area of interest. And within the Open Data Cube, there is a library or there's a method to actually pull in specific data types. And you can actually pull in multiple data sources at the same time. So you have Landsat stored in one variable, for example, you have Modis or Sentinel stored in one variable, and you can run the same drill down command across all of those products. So then you have data products for Landsat as well pulled in, and for Sentinel, and as well as for Modis as well. So it's all combined together. And that's actually the highlight of the data cube itself, or the Open Data Cube itself. So whatever you said can be done on the Open Data Cube. Yes. I think those are the questions I noted down, at least when you were asking, but hope that clarifies. Okay. I see some in the chat. Yes, the Earth Engine has now moved. So initially, I was part of the Data Cube, the Open Data Cube project in IIHS Dehradun as well, under the leadership of the Geoinformatics department at IIHS. And back then, this was one of our major concerns, saying that one day, eventually, Earth Engine will become paid. Back then it was not, and we were saying that the Open Data Cube is what the Earth Engine is, is supposed to be open source and things like that. So back then that was one of my advantages in my thesis when I was writing it down. This is literally this point, and then I guess 6 years later they have actually followed through on that. But I think for academics and researchers, there can be some limits. There might be some openings here and there, but it is a business in the end, like Dr. Shyam was saying. So Yeah. Yes.
Yeah, anybody else?
Hi, Amruth.
Yeah.
Yeah, so initially you mentioned that you were able to get some credits, right?
Yeah.
So these credits are offered to individuals or organizations. So that is one question. And
Okay.
the other question that I have is, so I have some experience working with Google Colab.
Okay.
So for the corresponding services, how would you compare? Like if you have used Google Colab, how would you
Yeah.
compare the two?
Okay. Yeah. So for the first question about the credits program, so this very specific credits program was for organizations, and the organizations could be either academic, institution, industry, or smaller labs, I can say as that as well. We have not seen an example of this for individuals specifically because it's quite a large sum of money. They offer like throughout I think every year they offer a few millions of dollars worth of credits for multiple agencies. So basically there is a short list of, I think 10 or 20 different organizations every year for the run of these credits. And then these credits last for 3 years. Or that was the actual program that was sponsored from GEO and AWS. So the credits last for 3 years, whatever that you're allotted. And then, anything, if you utilize more than that, you have to pay for it. But I don't think I've seen this for individuals, and they fall under very specific themes. So it could maybe one of the SDGs that are under control, or anything of that kind. So it's very specific to what theme they're following at a very different point in time. So I don't think they offer it for individuals as of now. I can link you to one of the managers over there who talk to us with that. So I think if you can email me, I can maybe share some details on this if you'd like. And I think the second question was about oh yeah, the Google Colab thing. Yes. So I wouldn't say they're similar. So Google Colab, I think, is a very, very small set of service, basically just one service to do one sort of task. I think when you're having Jupyter Notebook interfaces, yes, you have ways to sort of store data here and there, again, on your own drive, on your own Google Drive, right? You're not utilizing anything else there. Processing is limited as well. You cannot run high-level processing for a long amount of time. I don't think you can run machine learning operations for sure on Google Colab because it times out after maybe 20 minutes of high utilization. So there's a monitoring method that Google Colab actually, I'm pretty sure they use to limit usage because it's a shared resource across a lot of people across the world, and it would limit a lot of activity basically. That's one thing. And that's just one service, right? And you don't actually know how it's working, and you don't have any customizability or functionality there. But AWS and Open Data Cube within that it's much different. It's a completely different ecosystem itself. I would say that it has way more functionality than what just a Google Colab can provide. Again, that is heavily dependent on who's building or developing all of this for you, or you yourself doing it. What I would suggest that to see the difference is to actually go to the Open Data Cube website, download the libraries, install it on your own laptop, and just test it out. You can actually do whatever we talked about right on your laptops. So just trying out the Open Data Cube live, it might seem a little bit overwhelming because it's an open source software. I think that's just some hard misconception out there, but it's something worth trying out. You would see quite a big difference between the Open Data Cube and Google Colab in itself. I would suggest Google Colab for smaller activities, testing out a few things, running smaller codes here and there on a Jupyter interface. But an Open Data Cube is a different ecosystem on its own. Yeah.
Right. Okay. Thank you.
Yeah.
Anybody else? Participant?
I have one question. Sorry if I'm taking time.
Yeah, go ahead,
No.
Chetan.
Yeah. Amrit, can you share the slide where you showed the Oregon and Mumbai regions for the AWS?
Just yeah.
Yeah.
Can you see it? Yeah.
Yes, I can. So you mentioned that you pulled the data of which was stored on Oregon.
Yeah.
It's stored on Oregon server. So
Yeah.
this data you are talking about is the rasters of Landsat or Sentinel. So these will be the geotiffs.
Yeah.
Okay. So nowadays, as you mentioned that you are trying to move to stack.
Yeah.
And the Element 84, which
Yeah.
open sources stacks. So that means that this process can now be eliminated from the ODC.
Yeah, exactly right. Yeah. So our major concern actually was that we were planning actually as one of our roadmaps to have a lot of these satellite imagery locally available, not just for the IDC project, the overarching IDC project, but for every other work that we're doing in the lab. Because we just did a small cost benefit analysis to compute to see that, the time spent on getting each Landsat tile for whatever projects that we have and maybe storing it on a local server or the IT infrastructure that we have here in the lab, that would actually be much higher than storing how many ever terabytes of Landsat imagery on a cloud. And that seemed like a better option, I think, back then, before the stack was actually implemented. It's quite, I think, 2 years back. So it seemed like a better option then. And more importantly, it saved us time. It was costing us maybe around $200 to $300 to store, $200 to $300 a month storing all of these terabytes of data at a Mumbai server, compared to the time it would take to actually process all of the models that we're doing by pulling the data from the Oregon server, because it takes time to actually transfer and then make a sync and index the data and then run your processes. And since every hour is being accounted for on the AWS, it is actually much faster to put your data closer to where you are physically and then run your processes immediately and then maybe delete the data if you don't want it. So that actually was a very optimal method during that point in time.
Okay, yeah, got it.
Yeah.
Thank you.
Sure. Yeah.
Yeah.
Thank you. Thank you. I think Chetan, you got right your answer, right?
Yes. Thank you.
So with this, we'll bind the session. First of all, I thank Amruth for delivering a wonderful session on building the Indian Data Cube. It was very informative, the lectures, and it's very new topic for the participant as well. And with this, before the closing, I would also wish to everyone, each and everyone, for happy Christmas and New Year 2023. So to all of you from the IEEE-GRSS Bangalore section. So with this, we'll close the session. Thank you all. Thank you, Amruth, for your valuable time and delivering the session. Thanks a lot.
You.
Thank
Yeah,
you.
sure.
Thank you, sir. Happy New Year. Happy Christmas
you.
to everyone. Yeah.
Thank you, Dr. Jaya. Thank you, Dr. Shyam. Thanks everybody for coming. Thanks for having me. See you all next year. Bye.
Thank you. Bye-bye.